So we'll look into the concepts of waveguides here. And first, I would like to start with the concepts of how the waves are going to propagate in the rectangular waveguides. The first technique is uh, using transmitting the waves or the signals using transmission lines, right? We already saw that transmission lines had some issues, like only TEM can propagate, right. So now we have other useful waves, electromagnetic waves, such as TM, TE, etc. Right. So whenever you need that, right, you cannot use a two-wire system. You have to go for what is called as a waveguide, out of which the simplest one to study or to start with is a rectangular. So we'll start from there, right? So the first concept that we are going to look here is the wave propagation of waves in the rectangular waveguides. Okay, as the name suggests, the shape we are going to use is it will be rectangular, and the name also suggests that they are going to guide the waves, right? So you define how you want the wave to be propagated, right, in the given medium or given device will guide the wave accordingly. Okay, so that's the whole concept of waveguides. Okay, let's look at that. So before that, let's try to consider the waveguide first. All right, let's try to construct a waveguide. So we need the three axes. All right, so let me try to draw a coordinate system first. Okay, so this is what I want, out of which some part I don't want. Just okay, I'll redraw that. That was too huge. Just 1 second. Okay, so this is the coordinate system, right? We are going to use. So I'm assuming that the wave propagates along the z-axis, right? So like we did earlier, so wave is expected to propagate in the z-axis. So our assumptions of the axis will be like this. Okay, so this is one of the axes, and so this is what we call as, say, x-axis. Uh, axis, the vertical axis which we are going to draw, let's say this is the y-axis, and I'm expecting that this will be the z-axis. Okay, right, so let us try to create a rectangular space around, so something that will be something like this. Okay, I'll try to make it more wider. So what you do along this, along the x-axis, its dimension is what is normally, it's a breadth that is denoted as a. Okay, so this is 0, this is a is the breadth, is measured along this direction, and the width of this waveguide is along the y-axis, and that will be the width. Okay, so now let's try to construct the remaining parts of this by just drawing the straight lines. Okay, so parallel to the z-axis, that's all. Right, it's going to have, right, dimension, the length of your uh, sorry, the length of this waveguide can be, right, of any size, any length. Okay, so length does not matter. So what we are trying to write is the breadth and the width of the waveguide. Okay, it's a rectangular in shape, right? So you can see that this can be I'm actually trying to cut the waveguide here, so I'll show irregular shapes. Okay, right? So again, for simplicity, inside this, right? So here we are assuming that you have air as the medium. Okay, air is the medium which is going to conduct, right? So direction of wave propagation, wave will be entering from this side, it will leave from the other side. So our intention is that we want the waves to propagate through this along the z-axis and reach the destination with the less amount of power loss. Okay, whatever is the input power, we want that to reach on the other side. Okay, so air as dielectric I already mentioned, right? So now we want that this particular waveguide carries the TE and TM mode of TM modes basically, right? So let's start with the equations of TM and TE waves. Okay, so wave equations of, first let me write the TE wave. Transverse electric. So previously we used the transverse electromagnetic. So what was the condition over there, if you remember, right? What was the condition why we called that as transverse electromagnetic wave? Some component was missing. Yes, in TM, which component is missing along which direction? Yeah, can you see here? Yes, so along the direction, no electric, no magnetic. That's why TEM. Now I am saying TE, right? Transverse electric wave. In the sense, electric component should be absent, right? Will be present. Yes, yes, that's all. That's all. Right? So the equation for TE will be only in terms of Hz. Okay, so del square Hz. Again, directly writing this equation from our electromagnetic waves chapter. All right, right. So that is equal to minus of omega square mu into epsilon into Hz. So this is because, right, Ez equal to 0. Similarly, let's write the wave equation of Tm. Easy to recall, right? Very easy to recall because the Tm means no H in my equation. So it's the same equation with E. So del square Ez is equal to minus of omega squared into mu into epsilon times Ez, because H is not present. So once again, I'll write the reason here, because this is Tm, no H component along the z-axis. Okay, now, so let's do with one of them and let's, similarly, we can write the other. Okay, one of them we can do. We can actually write the conditions for one of them. Like for Tm, we'll start. Okay, so expanding the del square Ez in, again, since we have chosen the rectangular coordinate system for the representation of the waveguide, and we call that, okay, there is a, along x-axis there is a breadth of a, along the height, along the y-axis we have a height, that is b, and the waveguide has a, can have any length along z-axis along which your wave is going to propagate. This is what we consider, right? So uh, why we are considering the specific coordinate system, because this del square E can be expanded in various coordinate system. Okay, but I have to use the one which I'm considering. So I'll write here. So expanding this del square Ez in the rectangular coordinate system. So what is that? If you remember, this is partial derivatives. Okay, del square Ez divided by dou x square plus dou square Ez divided by dou y square plus dou square Ez divided by dou z square. Right hand side still remains same. Minus omega square mu epsilon into Ez. Okay, now again, I'm taking the concept from the electromagnetic waves. If at all you are considering the wave to be propagating along a particular axis, right, the double partial derivative along that axis is represented by the gamma square, which we had written earlier, the constant, right? So but I'll write, so but the dou square, okay, now you don't have to write a Ez, it's just dou square by dou z square is equal to the gamma square, right? This is applicable only for that direction along which the wave propagates. Other direction you cannot change, you have to keep it as it. So that means this implies, so dou square Ez by dou x square, dou square Ez by dou y square plus the gamma square times Ez, okay, equal to minus of omega square mu epsilon times Ez. Okay, now what I do, I'll take okay, I can see Ez common. So let's try to make another change here. So this implies the dou square Ez by dou x square, dou square. Yes, I'll bring to the left side so that I can try to write the most appropriate format. So plus the gamma square plus omega square mu epsilon times Ez equal to 0. Right, now we'll bring a constant into picture that's called as the h value, right? So this implies okay, let's try to write this is the final equation. Yes, that's the standard equation of the transverse magnetic wave. Okay, dou square Ez by dou x square plus dou square Ey by dou Ez by dou y square, sorry. Okay, only Ez is the one which we are considering, plus the this is h square. Okay, so h square times Ez equals to 0 is the equation of the TM wave, right? Again, I can solve for Ez to get an answer. We'll do that later. Okay, so this is what is the first concept. Similarly, I can write because the other equation is also same, right? So similarly, I'll write, now you see this is dou square hz by dou x square plus dou square my mistake, sorry. It is hz only because we only have the z component. Okay, so that is dou square hz divided by dou square hz by dou y square plus the same constant h square times hz equal to 0, right, will be the equation of our TE wave. Okay, now recall how did you solve the equations like this in the electromagnetic waves chapter of maybe the field theory or some other subjects, right? You had to use some standard equations, right? They're called as the Maxwell's equations. Have you come across Maxwell's equations somewhere? Right. So there are four equations, out of which two of them we are going to use to solve these cases, right? So using Maxwell's first equation. So what does it say? It is a del cross H equal to J times omega epsilon times E. In the sense, how do I convert the magnetic field to an electric field? Okay, or the otherwise, right? If you have electric field, you can convert into magnetic, but you don't use this equation for that purpose. You use the second equation. Okay, so as of now, H getting converted into E is what we are looking for. Okay, right. Again, if you consider this, if our intention is to find how they are related, you can use any of the equations, but right, as of now we are trying to convert. So what do we do? Let's try to expand. So del cross is a curl, right? It's a curl operator. So recall what is a curl operator. So again, we are restricting them to the H is the complete H, and E is the complete E. In the sense, all the components will try to write. Okay, later on we'll modify as per the requirement. Okay, so del cross H is what we are trying to write now. So del cross H expansion is I cap, J cap. Then you have a partial derivative dou by dou x, dou by, yes, dou by dou z. Then it is H. So all the H components, Hx along the first column, Hy along the second one, Hz along the third one. So take a determinant of this, you get the del cross H. On the other side, it is J omega epsilon times the electric field. Electric field has the following components, that is Ex I cap, correct, Ey, Ez, K cap, that is the E. So actually I can write in this way just to make sure that they are the vectors. Right. But now I have another thing to write. That is, you see this component, whatever I am having, right? That is actually minus gamma, right? Because dou square by dou z square was a gamma square that came because of this thing, right? So dou by dou z is minus gamma. So I have to remember that whenever I write, I'm going to apply this, this has to be a minus gamma. Okay, so what I do, okay, I'll copy this once again. Over there, I'll directly replace. Okay, so okay, we got it. Now I am changing only one value. Okay, that is dou by dou z is what I want to replace as minus gamma. So that will be the minus gamma. Okay, now I have to simply expand and compare both the sides. Okay, so that is, let's keep I cap. This is dou hz by dou y, minus of minus is plus gamma times hy, correct? That's the first term. Then minus j cap into dou hz by dou x. Again, this is minus of minus, so plus gamma times hx plus k cap into dou hy by dou x, dou hy by dou x minus dou. So that's the equation. Similarly, let me expand and write the terms on the right hand side. I'll write here. So that is with I cap, let me write all the terms. That is j omega epsilon into ex, right? Plus j cap into j omega epsilon into ey plus k cap into j omega epsilon ez. Okay, so what we are going to do, we compare. right? This implies we get the solution of the equations. That is, so first term, compare the I coefficients. That is dou hz by dou y plus, yes, gamma times hy should be equal to j omega epsilon ex. Okay, right. Similarly, the second equation will be dou hz. I'll move the negative to the right side. All right, so this is dou hz by dou x plus gamma times hx is equal to negative j omega epsilon times ey. Similarly, the third term should be dou hy by dou x minus dou hx by dou y is equal to j omega times, sorry, j omega epsilon times ez. All right, so this is the solution we get, right? Similarly, in order to get the other three equations, what you are supposed to do, you have to apply the Maxwell's second equation. Okay, so by using Maxwell's second equation, right? What is the second equation? It is the del cross E vector is equal to minus of j omega mu into h. All right, you see the change. We have mu coming into picture instead of epsilon. So that's the difference. Okay, right. So let's try to expand this in the same fashion. So that is I, j, k, dou by dou x, dou by dou y, dou by dou z. So just recall, I'll replace here itself. Okay, it's minus gamma, right? Do you want to write dou z and then replacing, or you are fine with this? You're fine, right? So I'll skip one step. Okay, so this is ex, ey, ez should be equal to minus of j omega mu into, now you see it is h, right? So this is hx I cap hy j cap plus hz k cap. Let us try to expand. So expansion results in the following. So I cap into, this is dou ez divided by dou y minus of minus plus gamma times ey minus j cap into dou ez by dou x minus of minus plus gamma times ex plus k cap dou ey by dou x minus dou ex by dou y. Okay, that's on the left hand side. On the right hand side, this is, I'll write a I cap outside. When the I cap goes out, this is minus j times omega times mu times hx, correct? Plus j cap into minus j omega mu hy. Okay, plus k cap into minus j omega mu into hz. Right. So this implies we can write three more equations. Right. So that implies dou Ez by dou y plus gamma times Ey is equal to minus j omega mu into this is hx. Is it okay? Similarly, the second, from comparing the second one, we get this. So that is dou Ez by dou x plus the gamma times Ex will be equal to, this is plus j omega mu times Hy. And the third one will be, that is dou Ey by dou x minus dou Ex by dou y is equal to negative j omega mu into h z. Okay, so let me give the equation numbers from the beginning. Okay, so let me call this is 1, this is 2, then the set of equations we derived earlier, let me call all of them as third equation, and the one we got now, let me call this is 4. Okay, right. Now, what we want is we try to combine, right, the equations we wrote just now. Okay, so that means I'll try to write a hy. Let me compare. So from 3 and 4, let me write something like this. So equation for hy. Okay, so this equation, I'm trying to refer to this equation, and in the third one, in the equation number 3, I'm going to consider the equation which is responsible for hy as it is. Okay, I can see hy as it is in this, right? So the first equation, right? Okay, in third, I'm trying to use the first equation, and in fourth, I'm trying to write the second equation. I'm trying to use them, okay, so that I can get an equation for the various components, right? Because as I know now, in case of this TM or TE waves, right, I may not have the components along the wave, along the direction in which wave propagates, but I'm definitely going to have the components in the other directions, right? I should be able to find out Ex, Ey, Hx, Hy, correct? So that is our objective now. So using 3 and 4, right, I just have to trace out which equation I'm trying to talk about, right? From the first equation which I have written, I'll try to write the equation for hy. Okay, so let me try to look at the equation number 1 and try to write what is the hy over there. Are you okay? So hy is equal to, so just above you can see, right, equation 4. Try to write a hy here from this, right? So hy is equal to, from this equation, try to write what is hy. Hy is equal to, take the j omega mu to the other side, correct? So that is 1 divided by j omega mu times left side, what you have, that is dou Ez by dou y, correct? Plus there is a gamma, I should divide gamma by j omega mu into Ey. Is it Ey? Sorry, it is Ex, my mistake. Because second equation I'm looking for, right? So it is Ex, right? So Ez and Ex. Is it fine? Okay, so I write this from equation 4. I also, now I substitute this hy in equation 3. Okay, so there is equation 3 which uses hy as it is. Okay, so I'll make a small change in my uh, representation. Just I'll make a change. So I'll write this like this. Let's make a change. So from 4, that you understand that. Okay, I'm writing this from 4. Okay, from 4 I write like this. So this is what I call 5. Okay, I'm substituting 5 in equation number 3. Right, one of the equation in 3 I can substitute hy as it is. Okay, so let's quickly try to find out which one we are talking about. So quickly go back and check where is hy as it is. That is the first equation. You can see hy as it is, right? I can simply put hy over here. Is that okay? Right, I'll put the hy in this equation in 3 first. Okay, so that means, so put this y over there. That means you see the first part of the equation as it is, that is dou hz divided by dou y, plus now whatever I'm writing is the function. Okay, there is a gamma there, so gamma gets multiplied, so that is gamma divided by j omega mu times dou ez by dou y, plus again gamma gets multiplied, so gamma square, right, ex divided by j omega mu. This should be equal to the right hand side. What is the right hand side of that equation 3? That is j omega epsilon times ex. Okay, this is what is my updated equation. Now what I try to do, right, I'll try to take the ex outside, because I can say ex common on both sides, on the, in the sense one term here, one term here, right? I'll try to move the ex terms to the same side. When I move to same side, I can definitely take out the ex, right? So that means this implies, I actually I'm skipping one step. I'll write the compressed answer. So ex into moving the terms to the same side and then taking the ex common. So see, there is a positive term, that is j omega epsilon, right? And the whatever is on the left hand side in the previous equation moves to the right side with the negative sign, correct? So that is minus of gamma square divided by j omega mu. All right, so this is equal to, write the remaining term. So there is a gamma by j omega mu dou times e z by dou x, plus this is dou hz divided by dou y. Okay, I can see that j omega mu in the denominator will multiply. So multiplying by j omega mu, right, to both sides. Multiply by j omega mu to both the sides. So what do you get? There is ex. So you see the j omega mu epsilon. So you see that j square is -1. I can write a minus there. J is gone. Omega is into omega is omega square, right? Mu into epsilon. There is already a epsilon present into mu. Similarly, for the second term, you see, right, I multiply by j omega mu, it will cancel, correct? So I have just minus of gamma square. Should be equal to, on the right hand side, this gets cancelled, right? So this is simply gamma times dou ez by dou x plus j omega mu into dou hz by dou y. Okay, we are coming to the last step now. So that means this implies, you see, my intention is now to represent or to calculate the ex, because ex is on one side. I'm trying to write the ex in terms of ez and hz, correct? So this implies, so what is this term? Can you tell me? What is this term? Correct? It is h square. Correct? Right. Minus of h square. So I can directly write, therefore, Ex is equal to, I'll simply take the minus h square to the other side. Is it okay? So Ex is equal to, this is minus gamma by h square times dou Ez divided by dou x. Okay, so this is minus gamma by h square dou Ez by dou x minus j omega mu by h square. I can take 1 by h square outside. That's also fine. Okay. Dou hz by dou y. Okay. So you see, we calculated, right, one of the component. Why we did this much calculation is because of one reason. I know that in case of TE or TM, I might have only EZ or only HZ. We didn't want to do two derivations. We wanted to compress it into one derivation. All right. You see, now Ez is 0 means just eliminate this term. Only this exists. Okay. Only that is the equation for Ex. Right. If at all you are using the transverse magnetic field, TM wave, you see this is not going to be present, right? Because Hz is 0. Hz is 0 means this is not going to come. Only use this equation, you get Ex. Is it okay? So that's our motto. We didn't want to do two derivations, right? Even if you go for separate derivation, then also it's going to be very tedious. So, right? So we did it in this fashion because of this. Now you see, right? I can actually write similarly. I have to do this derivation, this part of the derivation once again, right? Using, I have to use another equation. That is, use this, get equation for hx. Right? Now you see in equation number 3, which of the equation, right, has hx, where you can substitute the hx directly. Okay, you can see that hx can be substituted for this, the second equation. It's actually the same procedure. You don't have to change anything out of it, right? The same, very similar steps, and you will be able to calculate the equation that I'll directly write. Okay, so similarly I'll write, because of the mathematical steps being very same, I don't have to show this. Okay, I can directly write the following equations, right? So that is one equation you get for Ey will be equal to minus gamma by h square dou Ez by dou y plus j omega mu divided by h square into dou hz by dou x. That is the equation for Ey. So again, here also you will be seeing the same thing, right? So if hz is not there, remove this term. Transverse magnetic field, right? At the same time, transverse electric means cancel the first term. Okay, right. Similarly, let's go further. You see, you need to calculate 4 components, correct? So hx hy, let's write the hx equation, right? You need to find out use the third equation to do this job. Okay, so that is hx is equal to, you get this answer, minus of gamma by h square dou hz divided by dou x plus j omega epsilon divided by h square times dou Ez by dou y. And the final answer, hy will be equal to minus of gamma divided by h square. This is dou hz by dou y minus j omega epsilon divided by h square into dou Ez by dou x. Right. That means if you know the Ez and Hz or one of them, right, you will be able to calculate the other four components of the wave that is propagating within a rectangular waveguide. Okay, so this is very important because whenever we want to calculate any we know one of the component and we know that it is T wave or TM wave, it is obviously it has to be represented using other components. So to calculate that, we use these four equations, right? That's actually the solution of the wave components, okay? Electric and magnetic field components inside the waveguide. So this is considered as the first concept under the rectangular waveguides.